Hello everyone and welcome to another section of the lecture series on measure theoretic probability. So today on lecture 7 we will be talking about denumerable probabilities and independence. Remember that throughout this lecture we assume that we have a probability space whereby we have the sample space, we have the collection of events in the sample space, and we have a probability space. But here we put all of these three things together and we call them the probability space. The reason being that P is defined on on F, and F is a collection of events from the sample space, and F, all events in F are measurable. That's why we can put a measure on it. So here the measure that we specify is the probability measure. So we call these three things together as the probability space. Note, F is a sigma field, and as we move forward we wouldn't be actually writing this, but all sets will be assumed to be in F unless otherwise we specify it. So definition, some simple things we would like to actually talk about is the conditional probability. What do we mean by conditional? By the word, we know that we have to condition something on. If you have something, it should be based on something. Okay, so you condition something on another thing. So we are saying that if A, which is a set or event in a sample space, is such that it has a positive probability measure, that's probability of A is greater than 0, then we define the conditional probability of B given A by probability of B given A to be equal to that is the probability of the intersection over the probability of A. This is the reason why we need A to be positive, because we can't define something over over 0. So we need the denominator to be greater than 0. Okay, so anytime we define a conditional probability and you don't specify that probability of A is greater than 0, then of course we can have probability of the empty set, which is 0. Okay, so we have to be specific that the probability of A should be greater than 0 for this to be defined. Equivalently, we can actually do a cross multiplication whereby we have probability of A multiplying the conditional probability, and therefore the probability of A intersection B will be equal to the probability of B given A times the probability of A. We call this the multiplicative rule. Let's try some example to actually understand our definition. So here we are saying that let L be some kind of event, that is, this event is maybe born in a long month. So, and R born in a month that has letter R in the name. So the long month will be a month with 31 days, and born in a month with R, I believe, is much more understandable. So here we ask ourselves, what is the sample space? What is the probability of R? And what is the probability of R given L? I believe answering this will help us understand what we're actually talking about. So let's check some answers from these questions. Okay, so A, we know that the whole space we are talking about is like the months in a year. So we have January to December, and we know that the total number of months in a year is 12 as indicated. So now we want to find the probability of R. This implies that the probability that a month has R, the name R in it, is we have 8 of them, and it is 8 over 12. So if you reduce it to its simplest form, we get 2 over 3. And here, remember that the first one, it wasn't conditioned on anything, so we use the whole sample space. But here we condition it that, let's say if you have probability of R given L, then we wouldn't actually focus on the total number of months in a year, but it should be with respect to the long month, whereby we have R in their name. So the long months, those with R in their name, they are 4. So we have 4 over 7. That's the probability of R intersection L all over the probability of all over the probability of L. So if you take this down, you're going to have 4 over 7. Okay, let's talk about something more interesting again. So we know of law of total probability. What do we mean by law of total probability, and what assumptions needs to be satisfied to be able to apply the law of total probability? So we say that if you have events A1, A2 through to infinity, and they are partitions of the sample space. What do we mean by partition of the sample space? This implies that if you have these events, then their union should be equal to the sample space involved. And secondly, if you pick any of these two events, they should be disjoint, implying that the intersection should produce the null set for I not equal to J. Alright, then if we talk about any other events that intersect all of these partitions, then the probability of B is equal to what? The sum of the probability that B, the sum over the probability that B given AN times the probability of what? AN, each of the AN. So if you sum these, so if you have sum of 1 through to infinity, it's the probability of B given A1 times probability of A1 plus probability of B given A2 times probability of what? A2. As you keep on summing them, then this implies that we have the law of total probability of B. Independence. What do we mean by independence? Okay, so we are saying that A and B are said to be independent if and only if this condition holds. If you take the probability of the intersection, it should be equal to the probability of A times the probability of B. That's the product of their individual probabilities. For events of positive probability, then remember that the conditional probability of their conditional, like the probability of A given B, is equal to probability of A, or probability of B given A is equal to the probability of B. Because since they are independent, we don't need information from B to find the probability of A. Then it implies that probability of A given B is A, and probability of B given A is probability of what? B. Alright, so let's take some examples and know how it actually works. So example, suppose that we toss 2 fair dice. So if we toss 2 fair dice, we have 1 through 6 here and 1 through 6 down. If you actually pair them, you're going to get 36 outcomes. So E1 is the event that the sum is what? 6. So if you pair them, which of them actually, when you sum them, you get 6. And F is that the first die is what? Is 4. If you roll them, the F is the event that we get the first die to what? To be 4. Okay. So let's answer some questions and I hope we will be done. So question 1. We ask ourselves, are E1 and F independent? This implies that you have to apply the definition for 2 events to be independent. We need that the probability of the intersection should be equal to the probability of the individual events. Alright, so we take the probability of E1, which is 5 over 6, 5 over 36. The probability of F is 1 over 6, and the probability of the intersection gives us 1 over 36. So we realize that probability of the intersection, which is equal to 1 over 36, is not equal to the 5 over 36 times 1 over 6, which is the probability of the individual events. Hence, E1 and F are not what? Are not independent, as you see. But we are going to use some kind of notation so that we wouldn't be writing independence, not independent. So if you see this kind of notation, A with this sign, B, notation for A intersection B, independence. A with this sign being crossed, it implies that A and B are not what? Independent. So let's try an example 2. Okay, if you have E2 to be equal to that, the sum is 7, and F, the first die, is 4. We ask ourselves, we have is E2 and F independent? So first of all, we have to find their individual probabilities and find the probability of their intersection. If they are equal, we are done. So probability of E2 is 1 over 6, probability of F is 1 over 6, and the probability of the intersection is 1 over 36. Note that 4 comes before 3, is not 36, because F is 4. The first die should actually be what? Should be 4. So that's our focus. Okay, so realize that 1 over 6 equals to 1 over 6 times 1 over 6 gives us 1 over 36. Hence, we certify the condition for 2 events to be what? Independent. We have probability of E2 to 1 over 6, F is 1 over 6, and the intersection gives us 1 over 36. Hence, E2 and F are independent. Alright, so with this, we do some kind of we generalize it in a way that if we have a finite collection of events A1 through to AN, They are independent. If we take probability of A1, A2 through to AN should be equal to what? The product of their individual probabilities. The product of their individual probabilities. If this happens, then indeed these events are what? Independent. We are going to actually talk about the infinite aspects in our next lecture. I hope you have a good day. Bye bye.